Uh, Good morning, everyone. So today's session is memory management in Python. So we'll see how the memory management is happens in the Python. So the topics we are going to cover today is we have four subtopics in memory management. One is arena, pool, block, and garbage collector. So we'll see one by one what is arena, what is pool, what is block, and what is garbage collector, and what it does with the memory management. Okay, right. So we'll proceed. So first is arena. So we'll see what exactly memory management is. So if you look at if we compare with the C programming, we have in C programming we have a dynamic memory allocation where we have few functions like malloc, calloc, realloc for allocation of memory, and for deallocating the memory we have a free function. So similarly here we have few methods to allocate the memory for each and every variable and object. Right. So we'll see one by one here. So here we are going to refer to the memory location by using the variable names or addresses, right? So here we have a variable and a memory location. So we are linking the memory location to a variable. So Python acts as a directory that keeps track of the correspondence between the variable names and memory addresses, and where the content of that variable can be found, right? So example, if you take, we have a mailbox, okay? I can refer to your mailbox directly by a number, that is the address, or by using your name to that particular box. So assume that I have a directory that tells me what box number is associated with your name. So that is how it has been mapped it. Okay. So Python allocates a fixed number of bytes of space in memory for each variable of normal integer type, which is known as int. So if you see in integer in C programming, you have 4 bytes. That is called 32 bytes, 32 bits. Okay. So now it has been limited there. So whereas in Python, we don't have a limit for int. Okay, because it is a dynamically typed. Okay, at the runtime, whatever the value it takes, it can be expanded. So that is a major difference between C programming and a Python program. So we don't have a restriction on the memory, right? So in Python, values of an integer is not restricted by the number of bits, and it can expand to the limit of the available memory. So if we say that 4 bytes, 32 bits, so we can, or 8 bytes are used for the Python floating types, that is 2 power 64 different floating point numbers can be represented. Okay. So here to know the size of the memory, how much space is been allocated, we can use a module called as sys module, which provides a function called as get size of function. By using that, you can know the how many bytes are been allocated or how many bits are been allocated for a variable. Okay. So when you want to write an efficient Python code, that is a memory efficient code, right, without any memory leaks, So we can do that using the one of the two methods, that is static memory allocation or dynamic memory allocation. So static memory allocation is being done at the compile time, dynamic memory allocation is done at the runtime. Right. So first we'll understand what exactly the memory looks like, not physically, or logically we'll see. Okay. Right. So if you compare, we are going to compare with the C programming because we already have learned C programming. So it will be easy for you to relate to the C programming memory allocation. Then we'll go with the Python memory allocation. Okay. So and see what we have, we'll see what is static memory allocation and dynamic memory allocation. So when you write a program, when you compile the program, it allocates the memory at compile time. That is in static memory allocation. So if you look at this, okay, we are saying int a equal to 10. Now a is a variable, right, which is of type int. So means the value 10 is been stored in a variable called a. So it has a fixed byte. Okay. So whenever you call this particular variable, it takes 10. So we have a static array only with the fixed size. Okay. And the memory is allocated at the time of compilation. Now when you see, and these are been stored in a stack. Stack is used for implementing static allocations. Okay. Now when you see for the dynamic memory allocation, memory has been allocated at the runtime, like malloc function, where we call that particular the memory as a heap. Heap is used for implementing dynamic memory allocation. So how we are going to do that? We are going to create a pointer variable, and we are going to allocate the memory address, like using the malloc size of how many bytes you want to allocate. That many bytes have been allocated and given to the pointer variable. So that is in C program, right? Right. So now why we are not using the pointers is because here everything in Python is an object. So object means it automatically goes to the dynamic memory allocation. Okay, because it is Python is an object-oriented programming language. Okay. So now in the Python memory manager will automatically reclaims the memory whenever it is not being used. Means it is also deallocates the memory. Whereas in C programming, we have to explicitly we have to do that by using the free method. Now here everything is been stored in heap memory. So the memory manager will keep track of which one is been used, which one is been not used for a longer time. So that will be automatically deleted. So that is called as a garbage collection. We'll see that topic in the next in the session going forward. So the Python manager manages the Python heap on demand. So whenever there is a more number of objects are being created, so it automatically deallocates the sum of the space and also automatically reallocates the space depending upon the demand. And the Python memory manager has object specific allocator. And for every object like integer, string, okay, float, we have a different size of object. So we'll see how exactly it will be doing that. So here the entire memory is bin, that is called as the raw memory allocator, interacts with the memory management of the operating system to ensure that there is a space on the private heap also. Okay. So here memory is then like if you see the analogy with the, if you want to understand how exactly the memory management works, so we will have a comparison with the real time scenario. So assume you have a empty book, that is memory is as an empty book. So you can begin, like you can think that computer memory is an empty book to write some short story. Okay, so we have we have multiple authors who can write the small stories on that in that particular book. Okay, so different authors will come along. Each author wants some space to write their story. Now, since they are not allowed to write on, like only one person is allowed to write at a time. So they should not override the other people's stories. Okay, so that is a condition. They are not allowed to write over each other, and they must be careful about which pages they are writing in, so that when they want to refer to the continuation of the story, is able to understand. So that keeping that particular track will be maintained by the manager. So the manager will decide which page to be given and which page not to be given. Okay. So since this book has been around for a longer time, many of the stories in it are no longer relevant, maybe sometimes. Like, so here it comes the concept of memory deallocation. So when no one reads or refers to that particular story, they are removed to make room for new stories. So the authors are like different applications. If you see, compare with the application real-time scenario and programming knowledge. So authors are nothing but the applications or a process. So whenever the application is running, they require some memory, right? So similarly, whenever an author wants to write something, he wants a book to be there and with some empty space. So the manager will decide which author to be written which where to be given the space. Similarly, here it is called as a memory manager. Okay. So the person who removed the old stories to make room for a new one is called as a garbage collector. So if you look at the diagram, okay. So here in the diagram, we are covering the three concepts: arena, pool, and a block. Okay. So we'll see one by one. So the Python memory manager manages chunks of the memory called blocks. So there is a least, it's the basic one. The base of the memory is called as blocks. Now, a collection of blocks of the same size. Here, if you need to remember, same size. Okay, same size. Right? Remember this. Uh, Same size. Okay, same size makes the pool. That is a collection of blocks. Now, pools are created on arena. Means our collection of pools are being created on arena. Now, each chunk, that is a block of 256 kilobytes of memory allocated on a heap. That is called 64 pools have been allocated. Okay. If the object gets situated, the memory manager fills this space with a new object of the same size. So we need to remember this particular term, right? It is allocating over fixed size. Okay. Right. So here arena are the largest chunks of memory. That is a bigger part. Okay. The overall page. So are aligned on a page bond in memory. A page bond is the edge of the fixed length. Okay. Again, here we are saying that same size or fixed length contiguous chunks of memory. So who is going to allocate this? So now this 256 kilobytes space has been allocated in the pool. Okay. This is nothing but a virtual memory page. Okay, it will keep track of which page to be referred. So all the blocks in the given pool are of the same size, same size of same class. Okay. So here, if you see this, if you are requesting in the bytes 1 to 8, the size of allocated is 8 blocks. 9 to 6, 16 blocks. So the size class will be given. Like if we keep on giving the next one, the sequence will be given. For example, if 42 bytes are requested, right? So 42 will come here. The data would be placed into the size of 48 blocks. Means the size class is 5. Now the pools are composed of blocks from a single size class. That is, if you say 8 bytes, it will be allocating all 8 bytes for that. Means the number of bytes have been allocated for that. If you see the previous one, right? So here 5 blocks have been allocated. So each pool maintains a double linked list. So here we are going to see some data structures concepts called as a double linked list or circular linked list, like so on. So each pool maintains a double linked list to other pools of the same size class. Means you want to go forward and backward, right? So that can be done using the double linked list. Means whenever there is space is free, you can go back and you can use that particular space. Okay. So in this algorithm, you can find available space for a given block of size, even across a different pools. So for that, we are going to use double linked list. So here we are using some terms called as a used pools. How to keep track of a used pools, or you have some terms called as a pool themselves must be in the three states. So what are those three states? Used, full, or empty. Now see what is each and every data. A used pool has available blocks for data to be stored. Okay, there is an empty space. You can use that. Full means the pool is completely full. There is no space for you to write in that particular pool. Okay, hence blocks are all allocated and contains data. Next, empty pool is till now no data has no data stored, not yet data has been touched or not able written even one time. Okay. Used means already it has been written and it has been got deallocated. So that is called as a used. A free pool will list keep track of all the pools in the empty state. So you have seen used, full, and empty state. So, but when do empty pools get used? Assume you need of 8 bytes of chunk of memory. There are no pools in the used pools of 8 byte size class. A fresh empty pool is initiated to store the 8 bytes. Like 4 bytes are there, but you don't have 8 bytes. So new pool is been created. From the new pool, you are going to be allocated. So this new pool then gets added to the used pool list. From the empty list, it will be going to the used pool list. Okay. So this is how you can see this used pools. It means it has been used. Free pools. So if you see the free pools, it is empty, right? No memory has been allocated or deallocated. So it is a fresh one. So in the used pools, you can see there is a fixed size. Here you have a different size. Okay. So here the blue color is called as untouched, means not yet used. Another color is free and another green is allocated, means memory has been there. Whereas here untouched means till now the memory has not been written there. Here this one indicates the memory has been written and again deleted. So that is called as a free space, not an untouched. Okay. So if you see this, the link, okay, here, this is as called as a double link. It means you can go in this direction or in this direction. Okay. So a block also like a pool, you also have a block. So a block also has 3 states: untouched, free, and allocated. Untouched, free, and allocated. Allocated, I told you, right? That has been there. Free means memory been allocated and deallocated. Untouched means not yet, not has been allocated. Okay. So the free block pointers points to single linked list. Means you're going to go from top to bottom, not right, not in the reverse direction. If you see the previous diagram, right? So here you have this block. So if you see this particular direction, so it is in a one direction, not a two-way direction. Like you see here, this is a double linked list and this is a single linked list. Okay. So list here, a list of available places to put data. If more than available free blocks are needed, the allocator will get some untouched blocks in the pool. It will take, if it will require more space, it will go to the untouched one instead of free. And the memory manager makes blocks free. Those new few blocks get added to the front of the free block list. And the actual list may not be continuous blocked. Okay, right. So the actual the list may not be continuous memory, like you can see here. Okay, there are some space has been allocated here, again here. So you can see there is a free space. Okay. So here is a linked list, single linked list coming from here. Again from here it going back here, right? Like this. This is a single linked list. Now what is an arena? Arena is, I told you, a collection of pools. Here also you have some space called as used, full, or empty. So the pools are used, full, or empty. It is the same way as what we have seen for the pools. Okay. And arena is organized in a double linked list. Right? You can see this here. So it can go forward and backward in the same way. And each arena, like here, how many free pools are there? The collection of pools are there. So here you have 0 number of pools because these are allocated and deallocated, allocated and deallocated. Here you have 3, 1, 2, and 3 are being used, and 1 is not yet been. So number of free pools are 1. Here you have 1 and 2, which is not yet at all used. So here you can see there are some of the pools have been used. So it is keeping track of how many pools are been free. So here we have seen the overview of the memory management. A few terms: arena, pool, and block. Right? Now, how you are going to use this? So the methods and variables are created in a stack memory. Block. Everything is created in the block. The stack frame is created whenever methods or variables are created. So these frames are destroyed automatically whenever the methods are returned. Like whenever the function is being completed, it returns the value to the called function. So then the memory is being get deleted. So similarly here, objects or the instance variables are created in a heap memory. As soon as the variables and functions are returned, the dead objects will be garbagely collected. Automatically, the data will be deleted. The memory will be freed. So we'll see what is a garbage collector. Garbage collector is a process in which the interpreter frees up the memory when it is not in use to make a available space for other objects, right? So here's the term which we need to learn is free up the memory when not in use. Okay. So how it is going to keep track? So it is going to use some of the variables, right? So it's this, we have, I told you, right, this model. So here you have 5 objects which keep tracks of the count, reference count and pointer to another type. So these 2 variables will be used to identify whether the variable is being used or not. Okay. So the reference count is used by the garbage collector. Then you have a pointer to actual object type. So object type is just like another structure that describes a Python object. Okay, if it is a dictionary or integer entity. So each object has own object specific memory allocated that knows how to get memory to store that particular object. And also deallocate the memory whenever it is been not used. So the reference count will be starting from 0 and whenever it is being used, it will increment by 1. Whenever it is not been used, it is decrement by 1. And it automatically becomes 0. So whenever it becomes 0, the count becomes 0, right? The object is deallocated. Means it is not been used for much time. Okay. So we'll see an example. So here reference counting. Okay. We have a reference counting. So when X is executed as an integer, object n is being created in memory. So if you see here, the count is become 1. Again, when Y has been created, Y equal to X, the count becomes 2. Okay, we'll see here. So the count you can see here. So here another is X has been allocated with 11. So automatically the pointer for this particular value gets decremented by 1 and he also won the count. Okay. So the reference count gets increased for a few different reasons. Like example, you have number equal to 1, 2, 3. So the reference count has become 1 means one time it has been used. Next time again, we are copying the same data to the another variable. So the reference count has become 2 because we are using this. Okay, we are using this particular number. How many times have been used? 2 times. It automatically increases if you pass the object as an argument. So the number this is again been used, right? So again the count is become 3. As a final example, the reference count will be increases if you include the object in a list. So this again one more time. It keeps on increasing. So to get the how many times it will be used, you can use this dot get reference count of that particular number. Okay. It will give you how many times it's been referred. Okay. So this is how the memory management works here. Right, we have seen a small example also and also the overview of the things. Right. Thank you. So we'll see in the next session, next video, we'll see about the exception handling. Right. Thank you.